Picture the scene for a second. You are sitting in a glass-walled conference room in some high-rise.
Ah, the classic high-stakes interview setup.
Exactly. The air conditioning is humming, your palms are just a little bit sweaty, and sitting across from you is a principal data engineer at a major tech firm, maybe a heavy AWS shop or a big fintech company.
And you've just finished writing out a solution on the whiteboard using PySpark.
Right. And honestly,
Yeah.
you are feeling pretty confident. You walked them through the code. You loaded the data frame. You filtered out the bad data. You ran a complex join with a lookup table.
And syntactically, it is perfect. It runs, it produces the correct number.
But that is exactly the moment the trap springs.
Yeah, it really is.
Because the interviewer leans back, taps the whiteboard right where you wrote dff.join, and asks a question that has absolutely nothing to do with the syntax.
They ask, what is physically happening on the cluster when that line executes? And why might this exact code crash if I simply double the input size?
And the silence that follows that question, that is the massive canyon between a junior developer and a senior engineer.
It's a huge gap. Massive.
That is exactly the canyon we are crossing today. We are doing a deep dive into PySpark under the hood. We aren't looking at how to write the code. We're looking at how to engineer a production-grade pipeline.
We're taking a stack of interview prep material, architectural white papers, and documentation designed for senior-level roles, and we are distilling it down to the physics of the engine.
Because that's the mission today, right?
Yeah.
Separating the people who can make code work from the people who can make code scale.
I mean, anyone can Google how to filter in PySpark, but to build pipelines that handled terabytes of data without blowing up the cluster or costing the company a fortune in cloud credits, you need to understand three things.
The engine, the fuel, which is memory, and the roadblocks, like the dreaded shuffle.
Exactly.
So let's pop the hood. Let's start with the engine. I feel like the biggest misconception, especially if you come from a standard Python background using pandas, is how the code actually executes.
Oh, absolutely. If you're used to pandas, you're used to what we call eager evaluation. You type df.filter, and it happens right then and there.
Your computer just works.
Right. CPU cycles burn, memory fills up immediately.
But Spark doesn't work like that.
Yeah.
Spark is lazy.
Spark is incredibly lazy. And in the world of distributed computing, laziness is actually a superpower.
Okay, let's unpack this for the listener. Why is it a superpower? Why is it better to wait?
So when you type out your transformations, your filters, your maps, your joins, Spark isn't actually doing anything with the data yet. It's just taking notes.
Like a blueprint.
Exactly. It's building a recipe, which we call the logical plan. It only actually starts cooking when you trigger an action like a write command or collect or count.
So up until I say, give me the result, nothing has actually happened.
Correct. And because Spark waits, it can see the whole picture. It builds a directed acyclic graph, or DAG.
The DAG?
Right. By looking at the entire chain of operations from start to finish before it starts processing, the optimizer can make decisions that a human might miss entirely.
This is the Catalyst optimizer we read about in the source material, the brain of the operation.
Catalyst is the reason a senior engineer can write code that looks simple but runs insanely fast. Let's look at a concrete example.
Okay.
Let's say you load a massive petabyte scale data set. You write code to join it with another huge table, and then right at the very end of your script, you filter for just the sales in 2024.
If I did that in a standard script or a naive SQL query, I'd load everything, join everything, which is incredibly expensive, and then throw away 99% of the result because I only wanted 2024.
Which is a complete disaster for performance. But Catalyst sees the DAG, it sees that filter hanging out at the end, and it performs something called predicate pushdown.
Predicate pushdown.
Yes, it physically moves that filter operation to the very beginning, right down to the data source level.
So Spark only reads the 2024 data from the disk.
Exactly. It never even touches the rest of the data. It minimizes the I/O before the data even enters the system.
A junior engineer writes instructions, but a senior engineer writes intent, knowing that Catalyst will optimize the path.
That's a great way to put it.
Now, once Catalyst has this perfect plan, this optimized blueprint, it has to hand it off to be executed. And this brings us to a term that I see thrown around in advanced interviews constantly. Tungsten.
It sounds like a sci-fi metal.
It is pretty hardcore. Tungsten was a massive overhaul of Spark's physical execution engine. The goal was to get Spark performance closer to bare metal.
Essentially pushing the limits of the hardware itself.
What was holding it back before? I always thought Spark was just inherently fast.
Well, it was fast compared to Hadoop MapReduce, but it was held back by Java, or rather the overhead of Java objects. You see, Spark runs on the JVM, the Java virtual machine, and standard Java objects are heavy.
Heavy how?
Imagine you just want to store the string ABCD. In C++E, that's just a few bytes. In Java, a simple string object might take 48 bytes of memory just to store 4 bytes of text.
Because of headers and metadata?
Exactly. Headers, hash codes, object pointers, it's massive bloat. When you have billions of rows, that overhead destroys your RAM and kills your CPU cache efficiency.
And Tungsten fixes this.
Tungsten changes the game completely. It bypasses standard Java objects and manages memory explicitly using binary processing. It thinks in ones and zeros, laid out efficiently in memory, almost like C++ code.
So it's skipping the middleman of the Java object structure.
Effectively, yes. It uses off-heap memory management, and it combines that with whole-stage code generation.
What does that mean in practice?
Instead of running one operator, passing data to the next, and running the next, which involves a lot of slow function calls, Tungsten collapses the whole chain into a single, optimized function.
So if Catalyst is the architect drawing the blueprints, Tungsten is the construction crew using high-powered machinery instead of hand tools.
That is a perfect analogy.
Before we leave the architecture, I want to touch on one more thing that separates the juniors from the seniors.
Yeah.
The what if it breaks scenario. Because if I'm running a job on 1,000 nodes, something will fail. A hard drive will die. A network cable will get pulled.
Guaranteed. In distributed computing, failure is not an exception, it's a feature. And this is where lineage comes in. Because Spark has that DEG, that recipe we talked about, it creates resilience.
How so?
If an executor dies and loses a chunk of data, Spark doesn't have to restart the whole job from scratch. It looks at the lineage for that specific missing chunk.
It checks the notes.
Right. It says, okay, to get this block, I need to read this file and apply this filter. It re-executes just that tiny slice of work on a different machine.
So it's self-healing.
It is. And understanding that lineage is key when you're debugging why a job is stuck or why it's mysteriously recomputing things.
Okay, so we've got the engine. We understand the plan. Now we need fuel. And in the world of Spark, fuel is memory.
And this is where the rubber meets the road. This is where most jobs fail. The dreaded O, out of memory error.
I feel like every data engineer has lost sleep over an O. It's basically a rite of passage.
It really is. But the reaction to it tells you everything about the engineer's level. A junior engineer sees an OM and thinks, I need a bigger cluster, let's double the instance size, let's throw money at it.
The brute force strategy.
Right. But a senior engineer looks at the memory management strategy. They ask, how is my memory actually being used inside the container?
So let's break that down. How is memory divided inside a Spark executor?
It's not just one big bucket where you dump everything. The two most important regions you need to know about are execution memory and storage memory.
Define those for us.
Storage memory is exactly what it sounds like. It's for data at rest. When you run df.cache or df.persist, that data lives in storage memory.
And execution memory.
That's for the scratch pad work. That's the memory needed to perform the actual calculations. Shuffles, joins, sorts, aggregations. You need space to buffer data while you're crunching it.
So do they have fixed sizes? Like 50% for storage, 50% for execution?
It used to be static in older versions, which was a nightmare. Now, Spark uses a unified memory manager. Imagine a flexible wall between two rooms. If execution needs more space and storage is empty, it borrows that space, and vice versa.
That sounds efficient. Why does it cause problems?
Because of the eviction policy. The tension arises when you cache too much data. If you fill up storage memory with cached data frames because you thought it would make things faster, and then you try to run a massive join that needs execution memory.
There's a conflict.
Exactly. Who wins that fight?
Execution usually wins. Spark will evict your cache data, literally kick it out of memory to make room for the computation. But if there's still not enough room, you hit the danger zone. You spill to disk.
Spill to disk. That phrase always appears in red in the monitoring tools. Why is it so bad?
Think about the speed difference. RAM works in nanoseconds. Disk works in milliseconds. Writing temporary data to the hard drive just to keep the job running is thousands of times slower. So your job doesn't necessarily crash, it just crawls.
It becomes a zombie. A job that should take 10 minutes takes 4 hours. And this is the key takeaway. Caching isn't free. A senior engineer knows that caching is a double-edged sword. You only cache if you are going to reuse that specific data frame multiple times and if it fits in memory without starving the execution.
Sometimes it's actually faster to just reread the data from the source than to cache it and cause a spill.
Yes, that is a classic senior insight. Recomputing a simple filter might be way faster than the overhead of serializing data to memory, managing the cache, and potentially spilling to disk.
Speaking of managing memory, there's one more hidden killer in the notes. Garbage collection. The GC.
Ah, yes, the janitor of the JVM.
If you're writing standard Python, you don't usually think about this much.
No, but in PySpark, remember, your Python code is driving a Java engine. If your code creates millions of tiny temporary objects, maybe you're using a user-defined function that instantiates a new object for every single row the garbage collector has to work overtime to clean that up.
And while the janitor's cleaning,
The factory shuts down, you get stop the world pauses, the entire application freezes while GC clears the memory. If you look at the Spark UI and see red gaps where no tasks are running, that's almost always GC pressure.
so managing memory isn't just about avoiding crashes, it's about avoiding these hidden performance penalties.
Precisely.
Let's move to part 3, the roadblocks. We've hinted at it, but we need to tackle the biggest performance killer in distributed computing, the shuffle.
The shuffle is the most expensive operation in Spark, period. If you can avoid a shuffle, you avoid a shuffle.
Why is it so expensive? What is actually happening physically?
It involves all three bottlenecks:
Hmm.
disk I/O, network I/O, and CPU. Imagine you are doing a group by country. You have data for the US, France, and Japan scattered randomly across 100 different machines.
Okay, I'm visualizing that.
To group them, all the US records need to end up on the same machine, all the France records on another. This means every machine has to talk to every other machine. It's an all-to-all communication. You are physically moving terabytes of data across the network cables.
This sounds like a massive traffic jam waiting to happen.
It is. And while that data is moving, nothing is being calculated. The CPUs are just waiting.
So how does a senior engineer minimize this? I saw broadcast variables mentioned as a classic optimization in the source notes.
Broadcast is the best way to eliminate a shuffle for joins. Let's say you were joining a massive 10 terabyte table of transactions with a tiny 10 megabyte lookup table of store codes.
A standard join would shuffle both.
A standard sort merge join would shuffle both to align the keys. Massive network traffic.
And broadcast.
Spark takes the tiny table, sends a full copy of it to every single executor, and keeps it in memory. Now the big table can just stay where it is. Each chunk of the big table can look up the data locally in that broadcasted copy. Zero network shuffle for the big table.
That sounds like a magic bullet.
It is. Until it backfires.
That's always a catch.
The catch is knowing what tiny means. If you try to broadcast a table that is bigger than the available memory on the executors, say you thought it was 100 megabytes, but it's actually 2 gigabytes, you crash every single executor simultaneously. Immediate. OM.
Ouch. So you really need to know your data size.
You do. Although, this is where modern Spark helps us out. We need to talk about AQE, Adaptive Query Execution.
AQE, this is a newer feature, right?
Relatively, it's a complete game changer. Remember we said Catalyst plans the query before it runs?
Right, the blueprint.
While static blueprints are risky, what if your estimates are wrong? AQE allows Spark to change the plan during execution based on runtime statistics. It pauses at the stage boundaries, looks at the data that just arrived, and re-optimizes.
So it learns as it goes.
Yes. For example, if it starts running and realizes, hey, this table I thought was huge is actually small enough to broadcast after the filter applied, it can switch a sort merge join to a broadcast hash join on the fly.
That is incredibly smart.
It also fixes the tiny partition problem. If Spark creates 200 partitions for a shuffle, but the data turns out to be tiny, you usually end up with 200 tiny tasks that take longer to schedule than to run. AQE will merge or coalesce those small partitions into one chunk.
It sounds like AQE fixes a lot of the manual tuning we used to have to do.
It handles the low-hanging fruit, but it can't fix bad data distribution. Which brings us to the ultimate nemesis, data skew.
Skew. This is when the data isn't balanced.
Exactly. Imagine you are aggregating social media data by influencer. You have one user with 100 million interactions and millions of users with 5 interactions.
Right.
If you shuffle by user ID, the executor lucky enough to get the super influencer gets hammered with data. It has to process 100 million rows. Meanwhile, the other 99 executors finish the work in seconds and just sit there idle.
This is the straggler task.
The job is only as fast as its slowest task. You look at the progress bar and it goes from 0 to 99% in 1 minute. And then it sits at 99% for an hour. That is skew.
That is painful.
Yeah.
So how does a senior engineer handle skew? Can AQE fix it?
AQE helps. It can detect that huge partition and split it into smaller subtasks. But sometimes even that isn't enough. Sometimes you have to do manual engineering. You have to salt the keys
Salting, like cooking?
a little bit. You take that massive key, the super influencer, and you add a random number to it. Influencer underscore one, influencer underscore two.
I see. So you artificially break it into multiple keys so they get distributed to different machines.
Exactly. You force the data to spread out, you aggregate the chunks in parallel, and then you remove the salt and aggregate the final totals. It's a two-step process. It's a manual engineering pattern that proves you understand how the distribution works.
That definitely sounds like an interview whiteboard problem. How do you handle a skewed join?
It is a classic one. If you can explain salting, you pass the senior check.
Let's move to the final section, production-grade engineering. We've talked about the engine and the tuning, but what about the actual data architecture? The source material mentions Delta Lake heavily.
In a modern stack, especially if you're on Databricks or Azure Synapse, you aren't just writing plain Parquet files anymore. You're using Delta Lake.
What's the elevator pitch for Delta? Why do we need it over just standard Parquet?
ACD transactions. It brings database-like reliability to file storage.
Which means
It tracks every single change in a transaction log. This prevents the classic data lake swamp issues, like what happens if a write job crashes halfway through? In plain Parquet, you end up with half-written corrupt files. In Delta, it's all or nothing. Plus, you get time travel. You can query the data as it looked yesterday.
But there's a specific optimization strategy mentioned here regarding Delta. Optimize and Zorter. What are those?
This solves the small file problem. This is arguably the #1 performance killer in data lakes.
What exactly is the small file problem?
Imagine you are streaming data into your lake. Every few seconds, you write a file. Over a month, you might end up with millions of tiny kilobyte-sized files.
And Spark hates that.
Spark hates that. Opening a file requires a network call, a metadata check, and overhead. Reading one single 1 gigabyte file is incredibly fast. Reading 1,001 megabyte files is incredibly slow. You die by 1,000 cuts.
So Optimize fixes this.
Optimize is a command that compacts those small files. It reads them all in and rewrites them as large, efficient files.
And Zorter.
Zorter is about how the data is sorted inside those files. It's a multidimensional sort. Think of it like organizing a library. If you organize books by genre, it's easy to find sci-fi. If you organize by author, it's easy to find Asimov. Zorter allows you to co-locate data, so it's efficient to find both.
So when I run a query filtering by date and customer ID,
Spark can skip huge chunks of files because it knows the data isn't there. It's called data skipping. A senior engineer sets up maintenance jobs to run Optimize and Zorter regularly. It's about cluster hygiene.
finally, I want to touch on the coding logic itself. The source notes list some specific problems that come up in interviews, things like sessionization.
Yes. This is where we see if you can translate business logic into distributed code.
Walk us through the sessionization problem.
The prompt is usually you have a log of user clicks. Group them into sessions. A new session starts if the user is inactive for more than 30 minutes.
That's tricky because you can't just group by user. You need to know the time difference between this row and the previous row.
Exactly. It depends on the sequence. A junior engineer tries to use a for loop or collect the data to the driver to iterate through it.
Which destroys the performance.
Right. A senior engineer knows how to use window functions.
How does that work?
You use the lag function. You define a window partitioned by user and ordered by time. You look at the timestamp of the previous event. You subtract it from the current timestamp. If the difference is greater than 30 minutes, you create a flag, say a 1. If it's less, you put a 0.
Okay, so now I have a bunch of ones and zeros marking the start of sessions.
Then, and this is the cool part, you do a cumulative sum of those ones. The running total becomes your session ID. As you go down the rows, the ID stays the same, 111, until you hit a new session flag and it bumps to 2.
That is clever. It turns a time-based logic problem into a mathematical operation.
And it happens entirely in parallel across the cluster. That is the kind of logic they want to see.
It seems like the recurring theme here is that the senior engineer is always thinking about the cost of memory, the cost of the network, the cost of reading files.
Absolutely. It's the shift from how do I do this to what happens when I do this. It's possessing a mental model of the cluster. When they write code, they aren't visualizing rows in a spreadsheet. They are visualizing partitions moving across a network, memory buffers filling up, and tasks being distributed. They code for the physical reality of the machine.
That is a powerful shift. It turns you from a coder into an architect. Now, before we wrap up, I want to leave our listeners with a final provocative thought from the source material.
Yeah.
We spent this whole time talking about how to optimize Spark, but there was one interview question that stood out to me as the ultimate curveball.
When would you avoid using Spark entirely?
Yes. When is the best tool, not the tool we just spent the last 20 minutes praising?
It's a great question, and the best answer is whenever you can. Spark has overhead. It has a startup time. It requires a cluster. It has to negotiate resources with Yarn or Kubernetes. If you are processing a 500 megabyte CSV file,
Just use pandas.
use Pandas, use DuckDB, use a simple Python script on a laptop. Don't spin up a 20-node cluster to do something a MacBook can handle in 10 seconds.
Don't kill a fly with a cannon.
Exactly. The overhead of distributed computing is only worth it when the data scale demands it. If you don't have scale, you don't need Spark.
I love that. The ultimate flex is knowing when to say no.
That's real engineering wisdom.
Well, that wraps up our deep dive into the engine room of PySpark. We hope this helps you look under the hood of your own pipelines, or maybe even ace that next interview.
Always look under the hood.
Thanks for listening, everyone. We'll catch you on the next deep dive.